Welcome to another interesting video for the normal force for the object on horizontal surface with the condition that the object has external force acting on it. So the objective of this session is to find the normal force acting on the object when there is a external force acting vertically down or acting vertically up, and then a special case when the external force is equal to the weight of the object, and to see pictorially normal force not being applicable when the two objects are not in contact. We do some numerical, and then also as a special case, what is the normal force when F external is acting as a pull at an angle or push at an angle. And then finally the summary. I would highly recommend you to go through my earlier video mentioned below for a proper understanding. So let's consider a block of mass m, which is on a horizontal surface, ground or earth. And we have to see what all forces are acting on the block m. Yeah. And there is one more force that you see in the picture, which is force external. So you can assume that there is some force acting vertically downwards on the object m, and it could be in the form of a push vertically down. Somebody can place their hand, or somebody can also keep another object on top of this object so that there is a external force. So when I say external, it means any force other than these two forces, yeah, other than the force due to gravitation by Earth and the normal force. So we have the external force acting on the object. Now, with respect to the free body diagram, let's talk about the vertical direction first. Of course, it is given that the block is not moving up or down. So therefore, there is no change of position in the y direction. And therefore, Newton's second law, when applied in the vertical direction, will look something like this. So the net force in the y direction, which is sum total of all the forces in the y direction, should be equal to 0. I don't want to make it very complicated, but since it's a vector notation, so ideally I should have written here 0 vector or null vector, but I don't want to make it complicated. Let's keep it very simple. So if we add up all the forces, so there will be a normal force which the ground will apply on the object acting vertically up, and the force external vertically down, and then the weight of the object vertically down. All three added together vectors should give me a 0 vector. Now, in terms of the magnitude, it should be pretty straightforward to understand. This is possible only when we have this condition met. The magnitude of all the forces acting in the vertical direction should be equal to the magnitude of all the forces acting in the downward direction, which means Fn equals to weight plus F external. And we know that weight is given by mg, so therefore Fn should be equal to mg plus F external. Now, how do you compare this case with my previous video in which I have not drawn any external forces? So just a block, if it is resting on the ground, then in that video I have shown Fn will be equal to mg. So the new thing that we have seen in this case will be if you apply any external force acting vertically downwards on the object, then the normal force will also increase by the corresponding force. So let's try to understand this with an example. Let's take mass of the object is 2 kg, yeah, and therefore the weight of the object will be 2 times acceleration due to gravity, which is, if I simply take it as 10, this will be 20 Newton. Yeah, and let's say it's given that the external force that is being applied has a magnitude of 15 Newton. Yeah, so if the condition for vertical equilibrium has to be met, then the normal force that the ground should apply on the block should be equal to 20, which is the weight of the object, plus 15, which is the external force, which is 35 Newton. So even in the figure, I have ensured that the sum total of the magnitude of these two forces in the downward direction should add up to the magnitude of the force in the up direction. So I've drawn them to the scales. So this should be 35. In terms of my units, it is around 3.5 centimeter, and this should be 20 Newton, and this should be 15 Newton. So 15 plus 20, 35 acting vertically down should balance the force, normal force, which is 35 Newton acting vertically up. So let's take up some questions now. Draw the free body diagram for each object. Let's focus on figure 1. So we have the object 1 of mass m on the floor. So what are the forces? Free body diagram for the object will look like something like this. The force due to gravity will be acting vertically down. My drawing may not be perfect, but I'll be giving you perfect diagrams drawn in the PowerPoint a bit later. First, I want to explain you the concept. So what is the force applied by the Earth on the object 1? So that will be nothing but the weight, and weight is given by the mass times g. So that's the downward force acting on the object 1. Should there be any upward force acting also? Yes, because the object is not moving in the y direction. So for vertical equilibrium, Earth has to apply a normal force on the object 1, and that magnitude has to be equal and opposite. So I can write this as normal force exerted by Earth on the object 1, and magnitude wise, of course, it has to be equal to mg. So what's the net force? So the net force in the y direction on the object 1 will be 0, because we have two equal and opposite forces acting on the object. So that's for figure number 1. Now let's focus on figure number 2. So this time a object of mass m, small m, it will be, the free body diagram will look exactly similar, except the values will be different. This time the mass is smaller, so therefore the force by Earth on object 2 will be the weight of the object given by small m times g. And since the object has a equilibrium in vertical direction, it's not moving up or down, so therefore there has to be a force, equal and opposite force, normal force by Earth on object 2, and that should be equal to, in magnitude, it should be equal to mg. And what's the net force? Again, because there is no movement of the object, net force along y direction has to be 0. Now, what's the reason for introducing the third picture? So this is, let's say we have another object 3. Yeah, this time it has a mass of m plus m. So again, the concept will be the same. So in the downward direction, there will be a weight. This time it will be bigger than mg, capital Mg or small mg. So this will be, let's assume this is the center of mass of the object 3. So force by Earth on object 3 will be equal to the weight of the object, and which in this case will be m plus m times g. And to maintain the vertical equilibrium, we have to have Earth applying an equal and opposite force. Yeah, so that will be normal force by Earth on the object 3. That has to be, with respect to magnitude, equal to m plus m times g. And of course, the same condition, because the two forces are equal and opposite in direction, so the net force in the y direction has to be 0. Now let's apply the understanding from the free body diagram of figure 3 to the stacking of objects, where we place one object on top of the other. So what figure 3 says is that if you have an object of mass m plus m, then the normal force by Earth on that object will be m plus m times g. So this should then also imply that if we had a mass m on the floor, and on top of that object, if we place smaller mass m, in that case, since the mass is the same, m plus m, in this new scenario, let me call it as A. So scenarios A and 3 are the same with respect to the total mass on the ground. So in this case also, without exception, this thing should hold valid, that the normal force by Earth, of course, it will be applicable on the object in contact, Nm will be equal to m plus m times g. And if I take the scenario B, so wherein I have a smaller object m, and on top of that I place a bigger object m, since the mass is the same, so figure B and figure 3 are identical with respect to the total mass. In this case also, the normal force by Earth, which for this time will act on the smaller mass m, will be equal to m plus m times g. So one important point, please remember that the normal force will always be exerted on the object in contact. So therefore, we conclude that the normal force by Earth in the three cases will be the same. That is for figure 3, figure A, and figure B. We can also generalize the understanding like this. So if there is a object with mass m, and the normal force by Earth on that object is mg, Then, if an additional force or F external is applied on the object, either through a push on the object or by placing another weight on this object, then the normal force by the earth on that object will also increase by the same amount. Yeah. So if F external is mg, then the normal force by earth on m will increase by the same amount, which is mg, which is m plus m times g. That's a very important key takeaway from this session. So let's take one interesting question. Draw the free body diagram for 1 and 2. So let's start with object 2 first. So we have a vertical equilibrium. So net force on both the objects in the y direction has to be 0. So free body diagram for object 2. So if I take this as the center of mass of object 2, what are the downward forces? So there will be a weight of the object, which I will put it as force due to earth on object 2, and that is the weight of the object, so I can write it as mg. Since it is in vertical equilibrium, the net force is 0, therefore there has to be equal and opposite force in the upward direction, and that force, maybe I can write it as normal force. But who is applying the normal force? So normal force is a contact force. It has to be applied by an object which is in contact with the object. So in this case, it is a normal force by object 1 on object 2. And because there is a vertical equilibrium, so that has to be in magnitude equal to mg, the weight. So this is free body diagram for object 2. Let's go to free body diagram for object 1. How does it look like? So if this is the center of mass of object 1, what are the forces in the vertical down direction? So there will be, of course, a force by earth on object 1, and that is the weight of the object, and that will be capital Mg. So that's the reason I've drawn bigger length in magnitude. So that's because this weight of the object 1 is more than weight of object 2. So any other downward force that is acting on this. So since object 1 is in contact with object 2, and due to action-reaction pair, there will be a normal force from object 2 on object 1. So what will be the magnitude of that force? So it will be equal and opposite to N12. So I can write it like this. This will be a force, a normal force from object 2 on object 1. And because these are action-reaction pairs, the magnitude of that is small mg. Okay, so there are two vertically downward forces, and therefore, for this object to be in equilibrium, vertically upward force has to be applied such that its length is equal to both the downward forces combined. So it may not be up to the scale. I'll be providing the PowerPoint diagram a bit later, but for the sake of understanding, there has to be a normal force by earth on the object 1. And because total upward force is equal to total downward forces for the equilibrium, therefore this has to be equal to mg plus mg, which I can also write as m plus m times g. And if you remember, it also matches the normal force by earth on the object 1 matches with what we have seen in the previous slide. So if there is a object of mass m plus m in any combination on the ground, then the normal force has to be given by this m plus m times g. So this is the free body diagram. Here is the free body diagram prepared in PowerPoint, and I have ensured that all the diagrams are up to the scale, which means if you see the length of NE1, that will be equal to the length of N21 and FE1 combined. So let's revisit the first slide I had shown. The key takeaway is if there is an external force applied in the direction of the weight of the object, then the normal force on the object increases by the same amount, as we have seen already. And another important thing is that I have not been mentioning anything about the horizontal direction because nothing in the horizontal direction is changing the vertical equilibrium, which means in the horizontal or x direction, the object may be at rest it may be in uniform motion. In both the cases, it will satisfy this. And if it is an accelerated motion, then it will satisfy this equation. But regardless, nothing changes for the vertical equilibrium on the y-axis. So what it means is that in the x direction, the object may be moving or may not be moving, but it has no impact as far as the normal force is concerned, because normal force is a part of vertical equilibrium, and none of the forces in the vertical equilibrium change with respect to anything happening on the x direction. That's very important. Now let's try to understand the normal force acting on the block on horizontal surface. So the additional condition given here is the external force acting on the object is vertically upwards. Yeah. So this is the external force acting on the block, which is on a horizontal surface or ground. And let's see what are all the forces acting on the object. For vertical equilibrium condition to be satisfied, which means there should be no net force on the object in the y direction, and we are assuming that the object is at rest, the sum total of all the forces, the net force on the object in the y direction, represented by sigma of all the forces Fy, should be equal to 0. So the three forces that are going to act, we know that whenever a object is placed, it will have its weight, which will be acting vertically down, and the force external in this case is acting vertically upwards. And we know that the normal force by the ground on the object will always be vertically up. So Fn, sum total of all these three forces should lead to 0. If all the three are in the y direction, then this condition of the vectors can be satisfied if and only if the forces acting in the downward direction add up to the forces acting in the upward direction, which means weight should be equal to normal force plus external. So which alternatively means Fn will be equal to the weight minus F external. And we know that weight is given by mg, so the condition essentially becomes Fn equals to mg minus F external. Let's take some practical values. For example, if I take the mass of the object as 2 kg, therefore the weight of the object, which is given as mg, will be 2 times, let's say I take it as 10, so that will be 20 Newton. Yeah. And let's say if the condition given is F external. So what is F external? It's a force which is being applied by some external agency, as the name indicates, on the object. Yeah. So how can you apply a force? You can apply, for example, a pull force. Somebody is pulling the object vertically up. Yeah. So that could be one example of F external. So let's say it is given that F external is 15 newtons. Yeah. So we have to find out the Fn. So from this equation, Fn equals to mg minus Fext, Fn will be equal to mg, which is 20, minus F external, which is 15 Newton. So it will be 5 Newton. Yeah. So pictorially, I have made it to the scale. So mg is 20 newtons. Yeah. And F external is 15 newtons. For the object to be in vertical equilibrium, it is a must that Fn should be equal to 5 Newton. So it's very important. The key takeaway from this slide will be, if there is an external force applied on the object in such a way that it is opposite to the weight of the object, then the normal force on the object decreases by the same amount. For example, if you would have applied F external as 10 Newton, then the normal force will be 10 Newton to balance the total of 20 in the downward direction. Again, it is very important to highlight what's happening in the horizontal or x direction. It really doesn't matter. So what we are saying essentially is that the equation for the vertical equilibrium, and therefore the normal force, does not depend on what's happening in the x direction. So in the x direction, there may be a net force. For example, there may be a net force. So I mentioned it as not equal to 0. So there may be a net force in the x direction, which means the object may be having a acceleration. So it really doesn't matter. Or the object may not have any acceleration. So that means object could be in uniform motion or it could be at rest. So these two equations in the x direction, they do not impact what we see in the y direction because x and y components are totally independent. And therefore, the normal force will always be given by Fn equals to mg minus F external. Now let's build upon further from the previous case. This time also we have the external force acting vertically up. We add one more condition that the external force, which is F external, equals to the weight of the object, so which is mg. So what happens? So the normal force will be given by mg minus F external. And if you put that condition, so Fn will be equal to mg minus mg, which is 0. So as I have shown in the picture, so if I take the example where we have the weight of the object is 20 Newton acting vertically down, if we provide a pull force or any external force which is matching 20 Newton equal to the weight of the object, then the normal force, as I've indicated with the blue dot, it's having zero magnitude. Yeah, so it's having zero magnitude. There is no normal force. So therefore, the normal force will be zero. Now, very important takeaway from here is if we have this such a condition that there is an external force and that is opposite to the direction of the weight that is applied on the object, then there is no normal force acting on the object, even though the two surfaces are in contact. Many times the books will write that the normal force will come in the picture as soon as the two surfaces are in contact. Now, with this example, I wanted to make a case where the two objects are in contact, but still there is no normal force. And what's the reason? Because I want to highlight from my previous video, there are two conditions for normal force to exist. Condition number one is the two forces should be in contact. Yeah, they should be in contact. And secondly, the two objects must be pressing against each other. If they don't press against each other, then there will be no normal force. Now, in this case, you see that the block is not pressing against the floor. Why it is not pressing? Because it is experiencing two forces equal and opposite. So these two forces cancel, and therefore there is no force being exerted by the block on the ground. And since there is no force, there will also be no normal force by the ground on the object. Yeah. So this is a special case from the previous slide. Now let's take the case where the object or the block is suspended by a rope. So the arrangement is such that the block is not touching the ground at all. Now, the point I'm making is since there is no contact between the block and the ground, so Fn is not applicable. Important to understand that if there is no contact between the surfaces, then normal force is not applicable. So remember, for the normal force to be applicable, condition one, the objects should be in contact with each other and they should be exerting force on each other, which is not the case here. The objects, the first condition is not met, and therefore there will be no Fn applicable, as I mentioned in the picture. And I have still mentioned the condition for vertical equilibrium only as a reference. So, meaning to say that since the object is at rest, so the resultant of all the forces in the y direction should be equal to 0, which means the force exerted by the string on the object, which is tension, plus the weight of the object acting vertically down should be equal to 0, which means the tension should be equal to mg. But remember that this vertical equilibrium has nothing to do with normal force. It's only for the sake of completeness of the slide that I've shown here. The important point is when there is no contact, there is no normal force. Now let's consider the case when the external force is acting on the object at an angle theta to the horizontal. So we have an object of mass m and we apply a force external at an angle theta to the horizontal. So again, for the vertical equilibrium, there is no net force acting on the object in the y direction. So therefore, it should satisfy this condition, and which means the normal force acting vertically upwards and the component of the force which is acting vertically upwards will be F external sine theta, and the weight force of the object acting vertically down together should add to 0. Now, before I go further, I need to explain what's happening in this triangle. So if this angle is theta as given, then this angle should also be theta. So that's because these are alternate interior angles between the two parallel lines. And given that this is theta, so the horizontal component will be F ext cos theta, and the vertical component of the force will be F ext sine theta. So since we are talking about the vertical equilibrium, so we need to focus only on the vertical components of the vectors. So in the vertical direction, we have F ext sine theta. Now, with this condition that the three vectors should add to 0, this will be possible if the forces in the upward direction add to the forces in the downward direction. So in the upward direction, we have Fn, yeah, and then we also have Fext sine theta, and in the downward direction, we have the weight W. So which means if you reshuffle, Fn will be equal to W minus Fext sine theta, and which in turn means Fn equals to mg minus Fext sine theta. So let's take some practical values where theta is 30 degree. So you must have seen this practical example pulling the grass cutter machine. You can pull at some angle. Let's say we pull it at 30 degree. Yeah. Let's say the mass is 2 kg. So that will be 2 times 10, which is 20 Newton, acting vertically down, which is the weight of the object. And what is sine theta? Sine 30 degree will be half. And let's say I'm pulling it with a Fext of also 20 Newton. Yeah. So Fext sine theta will be equal to 20 times sine 30, which is half. So this will be 10 Newton. Yeah. So the picture looks like this. So we have 20 Newton acting vertically down, and then we have 10 Newton acting vertically up. Therefore, the normal force, which I've drawn with the blue arrow, will be equal to 10 Newton. So Fn will be equal to 20 minus 10, which is 10 Newton vertically up. That's the normal force by the ground on the object. So key takeaway from here is if there is a external force which is applied in the direction opposite to the weight of the object, so in our case that component is coming to F ext sine theta, yeah, then the normal force on the object decreases. It decreases by the same amount. And what happens to the horizontal component? So as I mentioned, whatever is happening on the horizontal component is not going to disturb our condition and equations for the vertical equilibrium. So yes, definitely there will be a force F ext cos theta, which is acting in the horizontal direction, and therefore it has to be considered appropriately in the horizontal direction or in the x direction, which is not in the scope of discussion of this particular case. Yeah. All we know that any forces acting on the horizontal axis will not have any impact on the vertical equilibrium, and therefore it will not impact our normal force on the object. Now let's take the case of an external force in the form of a push acting on the object at an angle theta to the horizontal. So what is given is the same setup. Instead of a pull as compared to the previous slide, this time it is a push. It is a force acting at an angle theta. So using the same logic, yeah, this will be theta, and therefore in the triangle we will have horizontal component as F ext cos theta, but the component that is of interest to us is F ext sine theta, because that is the vertical component of the push. So if we apply the condition for the vertical equilibrium, so sum of all the forces should sum up to 0, which means Fn acting vertically up plus Fext sine theta acting vertically down plus weight acting vertically down. All three vectors, when we do the vector sum, it should be 0. Now, in terms of the magnitude, what it means is all the forces in the upward direction, so Fn is acting vertically up, should add up to all the forces this is algebraic addition to all the forces acting in the vertically down direction. So, which means Fn should be equal to mg plus f ext sine theta. Now let's take some values similar to what we took earlier. So if theta is 30 degree and let's say the mass is 2 kg, so this is 2 times 10, which is 20 Newton, the weight of the object, and what will be fext sine theta. So let's say I apply fext is also 20 Newton. Yeah. So fext sine theta will be 20 times sine 30, which is 1 by 2, which is equal to 10 Newton acting vertically down. So if you have 20 Newton vertically down, and then again 10 Newton vertically down, then in the upward direction, for this to be in equilibrium along the y-axis, the normal force has to be 30 Newton. Okay, so I just put it in the equation. So mg will be equal to 20 plus 10, therefore 30 Newton vertically up. Now, key takeaway from here, if a external force is applied in the direction of the weight of the object, then the normal force, now in this case, the component that we are talking about is fext sine theta. Fext times sine theta, then the normal force on the object increases by the same amount, which is fext sine theta. How about some case like if theta is equal to 0 degree? So if you're applying any push at 0 degree, or for that matter, pull also at 0 degree. So in both the, let's say you're applying push at an angle of theta degree. So sine 0 will be 0, and therefore Fn will be equal to mg. The same observation will be there for a pull also. And at 0 degree, so what we are essentially saying is that there is no impact of the forces which are acting in the horizontal direction. There may be a net force in the horizontal direction, or there may not be a net force in the horizontal direction. But as far as vertical direction is concerned, in case of theta equal to 0 degree, Fn will always be equal to mg. So let's summarize. As far as the magnitude of the normal force is concerned, if a question comes up, is Fn always equal to mg or more than or less, then the general equation that you can remember is the normal force will be mg plus or minus F external. And when do I use the plus sign? Use the plus sign if F external is acting downwards, same direction as the weight. Yeah, this is the direction of Fext. And when do I use the negative sign? This is applicable when Fext is acting opposite in direction to its weight. That means vertically. How about the direction of the normal force? It's always normal or perpendicular to the surface, and it is always opposite to the weight force of the object. Now, before I close the session, let's summarize the key expression or equation that we have learned in this video. Normal force will be equal to the weight of the object plus or minus external force. So if we go on applying against each of the condition, there is no need to remember this table by heart. You have to just keep on applying the logic. So let's go with the first one. If there is no external force, then we see clearly from this equation that normal force will be equal to weight, which means mg. Okay. Next case, F external acts vertically down. So I mentioned in the previous slide, whenever it is acting vertically down, take the plus sign. So which means Fn will be equal to mg plus F external. Now, next case, F external acts vertically up. Okay. And when it is vertically up, I mentioned take the negative sign. Therefore, the normal force will be equal to mg minus F external. Now, there is a condition I mentioned over here that F external is less than the weight of the object. As a sub case, if there is a Fext vertically up with the condition Fext is equal to the weight of the object, in such a case, this condition will be W minus W, which means the normal force will be 0. And how about the last case? Object is not in contact with the surface. So as I have explained earlier, the normal force in such a case is not applicable. Thank you for watching this video. Please like, subscribe, and share this video. and also kindly drop your comments. Thank you.